Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 26, 2025, just yesterday. The striking idea is simple and bold. Instead of forcing exact multi-token guesses, training a model to predict the order of upcoming tokens by proximity yields better language modeling, with consistent gains over both next token prediction and multi-token prediction across standard benchmarks and at larger scales. The paper is titled, Predicting the Order of Upcoming Tokens Improves Language Modeling, and the implications for model training are quite significant. The approach uses a single extra unembedding head, drops at inference, and proves more compute and parameter efficient, while improving perplexity and downstream scores. On X, researchers highlight that ranking upcoming tokens by proximity improves language modeling with comparable compute, using a ListNet style loss and a single extra head, and they report consistent benchmark gains across 340 million to 7 billion models. Engagement looks moderate, with about 40 likes on one post and low double-digit reactions on others. Also, the authors shared a GitHub repo. It's a compact landing spot with PyTorch and Triton code. You'll find ListNet loss implementations, both naive and diffused linear Triton version, plus utilities to convert token sequences to top targets, again in naive and Triton forms, and pointers to training code and checkpoints. Alright, the previous figure summarized the main idea at a high level. Figure 1 presents the end-to-end setup, which contrasts the standard next token head with the token order head that predicts proximity ranks instead of exact futures. The pipeline begins with a toy vocabulary and tokenized lyric, flows through transformer layers, and splits into two parallel unembedding heads. The right side highlights different targets. 1 hot vectors for next token prediction, and graded proximity scores for token order prediction, so the combined loss encourages both accuracy and useful ranking structure. So the previous figure contrasted target types. Figure 2 shows training curves for multi-token prediction with 16 heads, plotted as loss versus steps. The lowest curve drops quickly and settles near 1.1, while successive heads flatten higher, which suggests distant offsets remain harder and contribute little signal. The widespread between the bottom and top curves indicates an inefficiency because many heads plateau around 3, adding parameters without matching gains. Okay, the previous figure showed why distant multi-token offsets add little signal. Table 1 lists the training configuration across the 3 model sizes, which matters because capacity and batch shape affect auxiliary losses. The table reports hidden size, layer and head counts, sequence length, rotary position frequency, vocabulary, and the token order window of 4096. The right block covers optimization. Atom W with a cosine schedule, 10% minimum learning rate, warm-up of 1 to 2,000 steps, global batch of 128, about 200,000 steps for larger models, and gradient clipping at 1.0. Alright, the previous figure highlighted training dynamics for multi-token offsets. Table 2 reports benchmark results across 340 million, 1.8 billion, and 7 billion models, comparing next token, multi-token, and token order training. The table shows that token order training wins broadly, with larger gains at scale. For example, at 7 billion, it improves Lambda accuracy to 57.03, and Trivia QA exact match to 30.90. The consistent green deltas indicate stronger downstream performance, even when next token loss stays similar, which suggests a useful regularization effect. Wrapping up, 2 takeaways stand out. Predicting the order of upcoming tokens is an easier, richer auxiliary signal than exact multi-token guesses, and it delivers consistent benchmark gains while adding only a single extra unembedding that disappears at inference. The broader implication is simpler, cheaper training that generalizes better. That is it for the AI Research Roundup. I am Alex. Thanks for listening.